So, it's okay? We can start?
Yeah.
Thank you. So, today's topic is what I call basic change of variables. And the notation will be, the change is z goes to the variable w, which will be a function of z. And we do this all the time, even in elementary, high school mathematics. So, elementary example. Everybody knows, you write down x equals r cosine. And now the question is, in Germany, the angle is called phi. But in the United States, the angle is called theta. So who in high school had phi? I know you did. You had phi also? You don't remember? I will dedicate this to Germany. So that is it. That's that. And y equals r sine phi. Right? Now, if you wish, and that was my point last time, and I will reiterate my point of last time, you could consider this as just a formal thing. There are, in fact, well, maybe cosine is defined. 1, 2, 3, 4 things. So this is a change of variables from, you see, w equals w of z. This is the change of variables x and y are functions of r and phi. Right? And the way to think about it is formally, you have the xy plane, and you have the r phi plane. And it even doesn't make sense at 0, we find out. Well, r equals 0 is okay. No, it's even okay, I don't care. R equals 0. Everything is okay. Right? I think I can put any numbers in here, right? So, and somehow this is just a symbolic change of variables. And at some places it makes very good sense. Right? So, for example, what you often do is you put between 0 and 2 pi phi, and maybe r bigger than 0. So someplace here in the domain here, it makes sense. Now that's what I was trying to talk about last time, and I think it's so fundamental to understand what is a change of variables. And quite often it is really formal. Last time I pointed out you have the germs of holomorphic functions, but really you have these things regarded as power series. And therefore you can regard them as formal series. I mean, you close your eyes and regard as a formal series. I mean, there's nothing fancy here. Okay? Right. And I call this thing embedding z. Now this is an algebra mapping. This is, if you multiply two things as functions, they get multiplied here as a formal power series. If you take linear combination things here as functions, they get taken as linear combination things. So this is what we call an algebra mapping, because this has algebra structure multiplication and vector space structure. This has algebra structure multiplication and vector space structure. It's algebra. And mappings that obey this kind of structure we call algebra morphisms. So if you have this set up, you just have a power series here, and you consider it as a formal power series. It's nothing fancy. And it's an embedding, so this little thing here in the tech command, hook right arrow or a hook down arrow, in this case, yeah. It's an embedding of this algebra in this algebra. And really, when you don't worry about anything here, that's what you're doing, right? You don't worry about anything. These are just formal objects that have meaning in power series and so on. And this is a formal change of variables. Okay, so you go here. You go here. So we study this guy. We studied it last time. I'm sure you're bored by it, but I think it's worth pointing out. I'm sorry you weren't here last time, but that's okay. You can get the lectures. And so you study this guy. This is a formal guy, just some formal algebraic guy, and you try to figure out what to do with this. And you find out that if you have P of Z in the formal power series ring, and this thing is in the maximal ideal, so this means that it's just any multiple of Z. I'm reviewing now from last time. If you have any one of these things here, that's more or less everything else. This means the formal power series that start out with Z, you don't have any constant terms. So this is essentially everything. If you have something in here, then you can write it P equals Z. Now I'm going to scale it in my head so you don't worry about. I'm going to look at things which really start with Z. So I don't worry about the coefficient of Z here. If I change the coefficient here by a change of variables, it's only a linear change of variables, which I don't worry about. This thing is this, but I'm wrong about this. It vanishes at some order n. I'm going to call this the order of P. Can't read it. Z to the order of P. I pull that out of the power series times this thing, which is a unit. And then I pointed out to you that there is, and you know it too, there is a Q hat, so that you can write this thing in the formal power series ring as Z to the Q hat. So this is a fundamental fact. I know some of you here, I can look at your faces and know you very well, had my analysis 1 course. And I probably didn't emphasize this fact well enough. The most important function in analysis 1, well, the most important thing to do is to be able to take a root. Yes? You ask yourself, what is the square root? Okay, maybe you can say what it is, but what does it mean? What does it mean a number a, which is you take to be positive? What does it mean a to the pi? Yeah. What the devil does that mean? That's a fundamental question to answer. And you answer that question. Formally here, you can answer it. You have anything. This is just a formal thing. There's a unique guy which you write down by saying you want this thing to equal that. There's a unique guy. A unique guy. Just compare, I don't know what it is in English. Koeffizientenvergleich. Anybody know? What does that mean in comparing
Coefficient-wise.
Compare
the coefficients.
Comparing coefficients. So you write down the unknown coefficients of this guy and compare to what you have here, and you get the answer. Right? That's nothing to do. And then you say you don't like this. You call this thing W. That's just a name. That's a formal name. Yes? So W is equal to this thing. W is equal to this thing, which I'm going to call, which is, say, R of Z. Okay? And now, formally, you can write R inverse down. If you wish, I'll write it like this, equals Z. Formally. Do you understand what I mean, formally? You just write down this power series, and you want to write Z in terms of W. This is some long series. You just write it back. This is formally okay. Yeah,
How do we know that the inverse exists?
I just said to you, it is formally trivial.
So we just say it
Yeah,
exists.
no, I'm saying, if you don't believe me, write down R of Z and try to invert the process. If you, I get tired doing it, so, but it's Z plus A2Z squared plus and so on. And now I want to solve this for Z. I want a power series of W, which gives me Z. So that means I want a power series applied to this long thing, which gives me Z. Right? I mean, it's a terrible thing. It's a terrible job. But it's a recursive matter. So you just write down the whole thing as formal. You don't think. It's a recursive matter. You get it? This means R of W, that's some power series applied to this whole horrible thing, gives you Z back. I don't want to do it, but you will be able to write down the coefficients recursively. Right? Okay. So what you have here is W equals a function of Z. That means you have inverted the power series. So you're very optimistic. You should always write down with optimism. You have the variable, the linear variable Z gives you an embedding in the formal power series of Z. And you have the linear variable W. So this is a Z linear variable. And W linear variable. Gives you a formal power series embedding of the formal power series in this. This is a copy of the Z-plane, this is a copy of the W-plane. This is nothing other than that. Do you understand? Right? Now, again, in elementary mathematics, you want to relate the Z-plane to the W-plane. What is a relation of the Z-plane to the W-plane? A relation of the Z-plane to the W-plane is known as a function. It is a graph. A function is a graph, right? That's all it is. And in your Mickey Mouse mathematics, which is not so bad in this case, you write W is a function of Z. Well, in high school you wrote Y is f of x. Y is f of x. That means the points in this graph are Z, W of Z. You want to relate these variables. You want to change the variables, if you can. I just did it in an example. Here is the way you change variables here. Here is the way you change variables formally. And here, this mapping here is given by W equals P of Z. Well, no, maybe not. R. Lucky you didn't. Simple change of variables. I was only here, just only had to make one mark. Very lucky. Okay, this thing is invertible, so we say this is an isomorphism. I wrote down the inverse for it here. You just say this inverse thing means you apply this guy to this horrible thing and you get Z back. That inverts the map. That inverts the map like an idiot because it's formal. But the fact of the matter is, sometimes if you're lucky, you have the same map here. And what does it mean, lucky? It means, first of all, you start with a function. Let's start with, you want to get it, you start with a function here. The function is Z, is the order of the function. It's equal to 1 plus Q, which is, this thing is a unit. Then you say, well, we can take roots. Then you call this thing W of Z, and you did it. procedures here are convergent. Otherwise, these don't even make any sense. This doesn't make any sense at all in many regions. Right? This doesn't make sense in many. For example, you say, let me give you an example here. You have some terrible function which is called tangent of phi. Right? Tangent of phi you hate. So after change of variables, you say tangent of phi is, what is it, y over x. Now most people, including my grandson at age 6, don't mind y over x. If I give him 3 and tell him 2, he says it's 1.5. Yeah? You much prefer that to tangent of phi. You change variables from these two variables to these two variables. You prefer that. The same here. If this converges, you can change variables up here, and these converge. So it goes both ways here, it goes both ways here, this goes back and forth. These are isomorphisms. This is in the z variable, this is in the w variable. But this is highly nonlinear here. This is the linear coordinate in the z-plane. This is the linear coordinate in the w-plane. Please don't object to me writing the z-plane as one thing like that. That's the z-plane. Here's the w-plane. This is the change of variables. It may be some terrible thing. It doesn't even exist out here. Maybe it's terrible around here. Well, it doesn't look like this because it should be going through 0, right? Because that's the way things have been set up here. Okay? So it only exists local. It's local change of variables. And we proved last time that if this procedure is convergent, then you have the local change of variables, and taking roots is convergent, and changing this variable is also convergent. That means these inverse process. If this is convergent, then this is convergent. Okay? Now, another viewpoint. And this is more analytic. By the way, let me just say again what this means. It means if f is holomorphic at 0 and the order of vanishing equal order of vanishing of f at 0, at 0 is, I call that O of f. Then, after change of variables, f equals w to this order. Isn't that what I just proved? After change of variables, so this whole business of complex analysis complex analysis, the only invariant really is the order of vanishing in the local theory. So the only local functions, up to constant scaling, you have the local function 1, the local function w, the local function w squared, the local function w cubed, and so on, after change of variables. You get it? Okay. So life is capitalistic. If you're willing to pay the money of changing the variables, which in my mind, the worst price is here, right? Yeah, here you pay a heavy price. You have to apply this thing to and formally figure out what that is, and it's terrible. And the same thing here, and the same thing here. Suppose you want to compute phi, the inverse, right? Suppose you want to compute phi, the inverse variable. It's not so easy. Maybe the inverse tangent plays a role here. I hope. So phi, you see the inverse change of tangent is tan inverse of y over x. That's what I did here in this formal change of variables. Yeah, you get it? Okay, good. So after conversion change of variables, you only have these few functions. One to constant, up to constant multiples, up to constant linear change of variables, which is nothing, just multiplied by constant. We have these few functions. Yes.
So could you explain again what do you mean by f equals w to the OF?
That's what I mean.
Could you explain the notion again?
Okay. What I mean is, I can choose a variable w so that f equals w to the OF. Okay. Another more intuitive, more pleasing statement is that this formal change of variables, which you understand, I think, lifts to a convergent change of variables, which says that this mapping is given by, this mapping here, let's say, is given by f in W space goes to f, let me just write it, let's say, write it f of w on W space goes to f of w of z. Do you get it? So now that's a pullback, that pulls this back, that's an or. G of z on Z space goes to G of Z of W, because I go both ways here. Okay, so I change variables. And this change of variables, I even told you how to do it. Do it at the formal level and notice that it converges. And that change of variables is only good in a small neighborhood. I mean, who knows where it converges? I've done all sorts of terrible things, right? So you don't know where it converges, but it's okay. But for the dynamics, for the local aspects of the function, it's some linear coordinate to the nth power. Okay.
But in your picture that you're writing there, in the 3 line space, exactly, you basically replace z times 1 plus some q.
Yeah, that's the coordinate w.
And the whole thing is w then. Okay.
So w equals w of z. It's this inverted thing. Is z times 1 plus q of z.
Okay.
You should have a Q hat. You should have a Q hat.
And I should have everywhere q hat
No,
here, here, because I took the root to get q hat. Right. Now, I think it's very much worthwhile thinking about this stuff. The giants of our past talked about variables and change of variables, and I had, I'm somehow from the past, so many of my teachers routinely changed variables without telling me what the heck they were doing. And these routine change of variables is always something like this, which you all understand, which sometimes is formal, sometimes is not formal. You have to check, right? But in this power series business, it's okay if it's formal, then you just have to check where it's convergent, if it's convergent, and so on. So another viewpoint is more analytical. And for this, we call real analysis. Which maybe you find more appealing. And I just talked about it a little bit. This is now the x-axis in real analysis. And this is the y-axis. And you have the function y equals e to the x. Right? That means you have this function here, y equal e to x. It means you have a graph. That's what the meaning is of a function. That's e to the x in xy space. X is a variable, y is a variable. Right? And That's interesting because this is invertible. Right? This change of variables is globally invertible. All right, everybody sees it. You go up here to the graph and you get that, or you start here and you get this. What is it? It's globally invertible as a function from as a map, convergent map from R to R plus. All right. Sometimes these things are not surjective, sometimes they are. This is surjective on the R plus. Well, you can see it. It's globally invertible. And now you should be very intense about this stuff. You should move between algebra and geometry and analysis. You look at this thing and you say, I call it X. And it starts, if you add things, then you multiply it. That is a statement that it takes additive stuff, X of x1 plus x2 is multiplying what you get. Don't forget it. I come from the older generation where you even use graph paper that converts this stuff for you. I mean, it's just incredible. So, okay, so that preserves multiplication. This is addition, and this is multiply. Right? This is a group under addition, whatever, recall what that means, please. This is a group under multiplication. Right? You add to, it's a group. You have the inverse and you have all this stuff. It's a group. It's a fundamental concept, by the way, first written down in the 19th century. So it took a while to understand this fundamental concept. The wonderful thing about this guy is that it's an isomorphism. This guy is an isomorphism because all you need to check is that it's injective and surjective. Okay, it's injective, you see it. If you have two different values of x, then they go to two different values of y, and you could clearly see that you get everything in R plus. So this thing is an isomorphism. Now, some of you people ask me questions about analyticity, and you should write down in this case, this is real analytic. Yes, maybe you were one of the persons.
Yeah, what's the difference between isomorphism and bijective map? Because
Yeah, thank you. First of all, it is bijective. Yeah. And the word isomorphism relates to the in this case to the algebraic structure, so it's smooth and bijective, and it relates to the algebraic structures. It means it has an inverse mapping because it's bijective, and the inverse mapping is also preserves the algebraic structures. So it's a very good question. When you use the word isomorphism, it means it preserves everything around. If I don't tell you what I mean by it, it preserves everything that's going on. And here you have addition, and here you have multiplication, and it preserves it. Word isomorphism. Thanks for your questions. Very good. Okay, it's real analytic, and everybody in the business knows what this is in a power series expansion. I can write it down in the formal power series expansion over the real numbers here, but it's a globally convergent power series expansion, starting with 0 in this case, and AN is even very well known. It's decays very quickly, and so this is globally convergent. Okay? And it's real analytic because these numbers are real, and everything's over the reals. Okay? Okay? But let me now tell you something. If you have a function which is a function of z and z bar, not just a function of z, and is a power series expansion a n m z n z bar to the n, so that's exactly how you write down such a function which is analytic on the complex plane, you see there's a z bar term here. So if you would expand this out, you would get x plus iy here, x plus minus iy here, expand all this stuff out. You say that these functions are real analytic. So somebody was using the word in some of your exercises. It's a good point. I can't remember who. What does it mean, analytic? Yeah. And if f equals f of z equals some a n z to the n, these are the holomorphic functions. That's the reason in the last part of the in the second part of the last century, we started calling these things holomorphic and not analytic. We call them holomorphic. Okay. These are functions of z alone, which are expandable in a power series in z alone. You see, or maybe you write complex analytic. Okay, so everybody here knows this real function. And he asked the question, what does it mean, isomorphism? Well, it means it has an inverse because it's bijective. And this inverse, we give a name to it, Ln. Right? This inverse thing, Ln. And in fact, Ln has a power series development about 0. It's much better you can't, Ln of 0 is no good because Ln is defined on R plus, and Ln of 0 is no good, so you just, all you need is a power series expansion start with x equals 0 starting at 1. So we expanded here, and you check out what this is, and it's probably something like, well, I don't know. I don't know.
Over n.
There's something like
n plus 1 and plus 1.
There's some place in n plus 1 probably.
Minus 1 to the n plus 1.
Maybe minus 1 to the
N plus 1.
n plus 1, x to the n over n. I think that's right. And the key thing is here you start at n equal 1, right? Yeah, because this function vanishes at 0. And this is trivially convergent because you can compare the geometric series. I mean, that's stupid. It converges. Not everywhere. By the way, it's a very dangerous thing at x equals minus 1. Because then you have ln of 0. So it converges. The best you can do is some interval that doesn't contain minus 1. Okay? And since that's what he was asking, ln inverts. Let me write it y1 times y2 equals ln of y1 plus ln of y2. So it inverts the algebraic operations. So it's a mapping which preserves the algebraic operation. Its inverse preserves the algebraic operation. It's smooth. It does everything. It's the first isomorphism in life. Remember my 8th grade teacher explained this to us in naive terms, which made very good sense and it still makes sense. So it's important if you ever teach school to teach things like this in a good way. That's great because now if you have a greater than 0, then we define a to the, I don't know, x equal something like x of x ln of a. Okay. Now that's not a theorem, that's a definition. All right? X makes sense, ln of a makes sense, a is positive, so ln of a makes sense, x is anything, a to the x is defined this way. Okay? Good. So this says that taking roots is finished. Whatever that means, over the reals is finished. This is an elementary thing, in my case from 8th grade, when my teacher explained the exponential map and logarithm in naive terms, but if you explain it in naive terms, you go back and forth and so on. You can explain it, and now for adults in terms of power series, there is no problem. So, let's go over to the complex plane with linear variable z. Linear coordinate z. Why not want to take a root? So I say, okay, let's define x of z. And so I define it, because I learned about it from my 8th grade teacher. So it's again, some power series. And this power series is the same power series. I just stick in z instead of x. And you do a stupid calculation and you see that the radius of convergence is infinity. You just check it. Right? I mean, you have to check that the nth root of a to the n goes to 0. So this converges everywhere. Okay. Great. And then you say, okay, well then x, and now it's a little bit his question, I'm going to be a little bit careful here. X is a holomorphic mapping from C to C. You put in a complex number, you get a complex number. In the usual language, exponential is a function. It's a holomorphic mapping on the complex plane. Okay. Okay. And now comes a fundamental idea. I don't know who had this idea, but it's one of these ideas that's trivial and beautiful and fundamental. Somebody wrote a stupid question, or naive question, or question -1. These are the good questions. And so you ask the good question here, x of z1 plus z2 equals x of z1, x of z2. So you write that as a question, and if you would see my scrap paper at home on my desk, which is piled, and half of it is wrong, and half of it is questions, and maybe 1/10 of it is answers, you would see my scrap paper is full of such questions. Even when I'm preparing elementary things. Well, what we do know is this. If we have the complex plane with coordinate z, here's x, and here's the number 1, and here's the number I, and here's z way out here equal x plus iy. Here's the x, we call it x axis and y. And now we study what happens, is that possible? So what we know is this is okay for z1 and z2 real numbers. So this thing is true if I'm on the real axis. So I look at this thing, I look at this identity more. Let's call this identity I. We don't know whether I is true. I'm just going optimistically calling it I. Why not? So I is holds for z1 and z2 in the complex plane, in the real atom. So now let's fix z1, c1, and let's say equal x1 in the real axis. So let's look at this thing just for that. x1 plus z2 equals, this is the identity that I want to prove, x z1 x z2. You got it? Fixed. Don't have any fear. It is a function of 2 variables. Think of it as a function of 2 variables, z1 and z2. I fix one of the variables x1, some number, and I ask this question. Okay? This question, and then I ask even a question, this is, maybe I call this identity sub x1. Right? If I stick in x1, this is identity x1. And then I ask the question, where does identity x1 hold? Well, I know where some of it holds if z2 is real. So we have the following situation. Let's write it down. We have an identity, so I make it even simpler. I say identity x1, I make it even simpler. It's a standard thing in life to make things simpler. Z minus x, x1, x, z equals 0. That's an identity. Where does it hold? It's a reasonable question, right? I should call it z here. Okay? This guy is holomorphic. And this guy is holomorphic in z. And this guy is holomorphic in z. Right? Yes.
It's an identity. Should it be 0 or 1? When we use 0?
0, because I just subtracted the right-hand side from the left-hand side.
Okay.
Well, I could do it by multiplication. I could do it by multiplication, but I didn't. I subtracted it. Okay? Multiplication a little bit dangerous here because I don't know what's going on with 0. Right? But I just subtracted it. Okay? This is holomorphic in z, and this is holomorphic in z. Okay? So then we have a question. You have a function h equals h of z holomorphic on the full complex plane. And h restricted to the real axis is identically 0. Right? It is, because of the reals, if you put a real number in there, you get identically 0. Here's the question. Is h identically 0? Right? This is the motivating question here. Right? You can imagine this happens all the time if you want to extend results from the reals to the full complexes. Right? I formulated it by pulling it over here, and this is a good formulation. Okay. And then, very interesting, historically, refined question. And all of these questions, that's the reason I really want you to learn to ask question -1, -5, -85, question 0, refined question, that D be connected domain in the complex plane. And F be holomorphic in D. Is the zero set of F, these are the set of points where F of Z equals 0, discrete. Okay. So let's look at these sequence of the questions where I claim all of you could have asked these questions. Right? Let's look at it again. I think it's very much worthwhile to look at. Based on wanting to take roots, we want to understand the exponential map. We write down the exponential map over C. This guy had better satisfy this identity, otherwise it's not going to be any good. Right? It's not going to be any good. So it needs to satisfy this identity. And we know this thing holds for numbers in the real. So we have an idea to fix one of the numbers being real and see if it holds for the next other number complex. So I reformulated it that way. Fix x, the first variable, to be real, and let the other variable run in the complexes. But then I reformulated that in terms of this. If it's identically 0 on the real numbers, then it's 0. And then I found really even general reformulation is if you have a domain and then you want to know the zeros of the function, what could it look like? Well, or f is identically 0. Right? I forgot you could have identically 0. I always forget this. Right? Yeah.
Could f be any holomorphic function?
Yeah. I just suddenly had a very optimistic, let us call it, conjecture. By the way, the word conjecture, I don't know, it looks French to me or Latin. The German word for conjecture, there's several, Vermutung and Mutmaßung. And you understand, if you know German, which most of you learned some anyway, the word Mut means courage. It means courage. Yeah, Vermutung, if you put fair at the front of a word in German, Vermutung, it means courage all the way to the end. Mutmaßung means an effort to make for courage. Those are the two words for it. I don't feel in the word conjecture, maybe you see it if some of you know Latin better than I do. Conjecture looks very Latin or French or it's interesting, I don't see the Mut, I don't see the courage in it. So this is the wonderful thing about German language. This is a Mutmaßung. It means I have courage to write this thing down and try to write it and see what happens. This is my conjecture. I write it as a question. If you write papers in mathematics, let me tell you about writing papers in mathematics. You see, a lot of authors are name droppers. They say, we consider the conjecture of Riemann. Yes. Then, if we consider the conjecture of Riemann, that means we're associating ourselves with Riemann and conjecture and so on. Okay. I think it's a much milder way of formulating, we consider a question that arises naturally in this matter. Yes. I like that formulation much better. We consider a question which arises naturally in this matter. Isn't that a natural question? Okay. Let's consider required. So suppose in the setting of the refined question, in the setting that 0 of f has an accumulation point. By the way, when you're writing mathematics, I'm a little sloppy here because I want to give you the idea of how I think. But what you maybe should write formally is proof by contraposition or proof by contradiction. I assume that the 0 set of f has an accumulative point, and oh no, I just assume that. That's not even a proof by contradiction. I'm just going to assume that it has an accumulation point. No contradiction here. No contradiction, it could be identically 0, that's my claim. Right? Okay, then you should draw the picture. Some terrible domain. It has some holes, it does some terrible things. Right? And it has an accumulation point. So this accumulation point, obviously you can call it 0. It's obvious, you can just translate everything over to 0 and call the accumulation point 0. Right. Here is 0. That says there's a sequence of points, Zn, which accumulates to 0. So f of Zn goes to 0, f of Zn equals 0. If f is is not identically 0, then f of z equals z to some order times a unit. You do nothing here, just that, right? Then f of zn equals 0 if and only if zn equals 0 for zn near 0. Right? So if you have a power series, it looks like that. If it's not identically 0, you can factor that out. That doesn't count because we're talking about it's 0. The only zeros it has is z to the power. You can have zeros other places, but then this power series expansion is not valid. Way over here it could have a 0. Right? In fact, you could have a sequence of zeros going to the boundary. Right? Okay. So if it's not identically 0, then in the neighborhood of the origin here, the only 0 of f is the origin. So that says what we've shown here is 0 of f not discrete implies f identically 0. So we approved this thing by contraposition. Okay. You okay on that? Yeah.
No, discrete meaning finite or countable?
Discrete means what it means. Neither. Discrete means that given a point in the set, there's a neighborhood about that point
Says that others don't lie.
which does not intersect the set. Discrete, yeah? Maybe, should I write it? So it's A is a discrete in a topological space X, if and only if for all A in A, there exists an open neighborhood U of A, open neighborhood of A with U of A intersect A and equal A. Okay, so it says nothing about finite or countable. But it does say something about it implies countable, as you know, because if you have a what do you call it, uncountable set, now, then you have some danger of having accumulation points automatically. This theorem, that we just proved, is called the identity principle. It's interesting that it's called that. That's a historical statement. This says F equals G on a set with accumulation. This is the way the giants of our past formulated this. Implies, well, if and only if F is identical to G. I'm applying it right like that. I subtract, it's his point, I'm subtracting G from the other side and looking at the function F minus G. Right. So if two functions are holomorphic, and yeah. Well, I haven't proved it yet. What have I proved here? Have I proved it? Oh, no, I'm not quite finished. Right? We're not quite finished. Let's follow that happens with me all the time. I think I'm finished, I'm not finished. By the way, that's one of the big mistakes in mathematics. You think you're finished proving you're not. Yeah, what do we prove here? We prove that if it has an accumulation point, then it's have proved F is identically zero near the accumulation point. All right, that's all we proved. All right? Okay. So, now let's see here. Now to finish the proof, we note that this set is automatically closed. You okay on that? The zero set of a continuous function, or the level set of a continuous function, is closed. That is a stupid remark. If F is zero on a sequence which has a convergence point, then it's zero at the conversion point. Right? So this is automatically closed. And now to show it is open.
Excuse me.
Yeah.
Do we then only assume that F only has or Z of F only has one accumulation point?
Say it again, please.
Because you said it's automatically closed since we have a sequence such as Z of N, such that F of Zn is 0. So
Then it's-
the limit point is contained.
It's also contained, yeah.
Right, but that means we only have shown it for one certain sequence.
Any sequence. Any sequence, no, so. I'm just saying that F inverse of 0 is the set of X or Z, doesn't matter, P, is a statement about continuous functions on topological spaces. Set of P such that Fp equals 0. Okay, this, and F is continuous. You agree this is a closed set. Why is it set? I just have to prove it's closed. I take a sequence which is in this set and assume that it converges to some point, then P is in this set. And that's what I just said. If it's 0 along a sequence and that sequence converges, then P is in.
Okay.
Right, that's how you prove something. That's, I'm being a little bit sequence oriented here, but it's okay. Okay. So, okay, so this set is automatically closed, and now it's closed, and I want to show that it's open. And so what I want to show it's open. Okay. Oh yeah. Very interesting. Very interesting. Let's look at this set. Are you familiar with this set? The interior of that set. Yeah? You're not, yeah? So this is the interior of this set. Okay? Maybe this is a better proof. Interior of this set. We already showed that this set has some interior. Right? Okay. Let's take this. This is the interior. This is an open set. I'm going to maybe change the proof around a little bit. This is an open set, right? The interior of the set is an open set. That's my definition. Right? The set of points that has a neighborhood which is in it. Right? Okay. Now let's look at the boundary of the interior. I like this much better. Well, I take the closure of the interior. I add some boundary. Right? What about the boundary of the interior? Here's the interior, and here's something on the boundary. Let's take a point on the boundary. It enters the interior like here. Here we have a Pn in the interior converging to P. Right? If I take something on the boundary of the interior. Okay. So that says, if something is the boundary, that implies that P is in the interior. Okay. So, you're not used to these arguments. I'm a little sloppy here, so let's go through it. Okay. Yeah.
So by showing that it's open, then you prove that it's 0 in every known domain or something like that.
So yeah, let's stand back. And he's asking, what am I doing here? I'm trying to think about this thing. All I know is that if it has an accumulation point in the 0 set, then that point is in the interior, right? Of that set. That we proved. Right? And now that means the interior is not empty, in particular. Right? And now I take the closure of the interior. Okay? you don't mind if I take the closure of the interior. If I take the closure of the interior, what I've done is added points at the boundary of the interior. These things are called accumulation points which are not in the set. Right? I've added points to that. But if it's an accumulation point, it's a boundary point, so it's an accumulation point of the interior, I apply the same argument. That says that if it's an accumulation point of the interior, you get an open neighborhood of that in the interior. So that says the interior is also closed.
What was your argument for the fact that the interior, not the interior, but the interior is non-empty?
Yes. Let's go through it again.
Yes.
This is a good exercise. Yeah. Okay. We assume that there is a sequence of points in the zero set which accumulates to a point in the zero set. Okay. Really accumulates. That means that that point, then I do a power series argument about that point. The function has a power series about that point. I called it that point 0. You don't mind. It has a power series, but I mean, unless it's identically 0, it's z to some order times a unit. Unit doesn't vanish, so we're talking about z to some order vanishing. The only point where that vanishes is the origin.
Why do you have it times the unit?
Because I haven't done the normal form yet, which we talked about at the beginning of the course. So I have the power series expansion a n z to the n, and it starts someplace, order of f. That's where it starts. And now I pull out that coefficient, so this is z to the order times whatever is here, and that thing doesn't vanish. Right, because its first coefficient is non-zero. Of course, that's only a local statement. Right? It's only a local statement. So this is a big remark or question. Yeah. How do I show that this thing has some interior? If it has an accumulation point, that point is in the interior. By the power series thing. Right? Okay, so it has interior. Now I look at the closure of the interior. If you have a point which is in the closure of the interior but which is not in the interior, it's a boundary point. That means you have a sequence of points from the interior converging to it, but I just apply the old argument again about the power series expansion about that point. Right? You have a sequence of points converging to this boundary point of the interior. Power series expansion says that can't be unless it's identically 0. So that means it's identically 0 on this. That means there's no boundary. That means that this thing is open and closed. Right? Well, the interior, I'm sorry, to be very precise, the interior is open and closed, right? It's very good. You haven't had much experience, but to me, I've lived so long in the topological world that I don't think about these arguments. But you haven't lived so long in the topological world, so you have to think about these arguments. Again, I look at the interior of the set. It's not empty. I go to the boundary of that thing. There's no boundary because I have the power series argument around it. That says that there's no boundary. It says it's both open and closed. Okay? Okay. What about its complement if it's closed? The complement of a closed set is open, right? Right? That says the domain D is the 0 set of this function union the non-zero set of this function. Yeah. D, let's write it. D equals the 0 set of this function. union, disjoint, D minus the zero set of this function. That's stupid, but this is open and closed. Therefore, this is open, and I've written D as a union of disjoint open sets.
But did we assume that it's connected?
Very good. Did you assume it's connected? No. In fact, we should experiment, and we have questions and so on, and we do all this stuff. And at the end, you say, okay, D is the union of two open sets, disjoint. And then you say, well, I could do a counterexample. I have two open sets, disjoint, and I define a function here to be 1 and a function here to be 0. And certainly the answer to this question is false. It's not identically 0, right? But it's his remark or question, did I assume D to be connected? Now that shows you I was a little bit smart here. I knew there had to be some, I knew about this bad example, right? I mean, you got a function that's identically 0 in one place and identically 1 on another place. Or some wonderful function on the other place, I don't know. Right? Okay. You're familiar with the statement. A set is connected if and only if it is never the union of disjoint open sets, which are non-empty. Right? You know that. And you know for domains or manifolds or anything, that connectedness means arcwise connectedness. That means given 2 points, there's a continuous curve between the 2 points. Make sure you know that. Yeah, I think you know that, but again, so it's interesting, right? So we had to do a little bit of thinking here. It's a little bit messy, but what we ended up proving is that is true for all x, okay? And now I do it for the other way around and so on, and we will have that this is essentially the argument. We will prove it's a homomorphism. Yes.
So actually, interior will be the full set, and we prove that
That's right.
it's 0 for all domains.
That's right.
Okay.
That's right. That's right. So if the statement is, well, here's a good statement. If the domain is connected, then the set is either discrete, so no accumulation points, or identically 0. That's the good statement. Okay?
How do we construct, I mean, we start with the first interior where we say there is definitely something for which it is 0, we start around 0 for that.
Yeah.
So when we now go to another point, and we say there's some point on the boundary on which we try to construct or have this convergent power series again, which has some order of convergence.
Right.
We need to have some
What,
order of
what-
convergence actually.
So, it's very good. So this is another point on the boundary. So you're asking about this argument here, right?
Yeah, so how do we...
So let's call this point in the complex plane Z0, okay? And it's an accumulation point because it's on the boundary. And I just said, okay, it doesn't matter, that could be 0, but I've already used 0 in some sense.
Yeah, right.
I don't care. Okay, but to make you happy, but I want to make you happy, is now I expand F here. It's an z minus z0 to the n. And it's the same argument,
Oh, okay.
right? So we factor out, this is Iglesias' thing, question. This is not anything serious to factor this out. It's just factoring out the leading term, right? And then times a unit.
You say you can have any change of variable in here.
No, that's very important to say. Since I am trying to explain to you an analytic viewpoint toward change of variable, I don't want to use change of variable here. I just factor it out like that. And from the point of view of zeros, this unit doesn't matter locally. So it is It is, from the point of view, we're using something like a normal form, but only for the zeros. So it's not very deep. Okay. Okay, great. I think we're starting to rule now. I like the vibrations here. Okay? It's because Crystal finally came today. Why were you sick? You weren't in Bremen? Oh, I'm sorry. It was a beautiful week. In terms of weather, I think. Yeah. Well, it's not so bad today. So thanks a lot.